Just mention that we have a couple upcoming PHIND seminars, one on August 17 from Aristus, and one on September 21st from Cindy. So looking forward to those in the future. And it's my pleasure to introduce our speaker today, who's Alberto Salleo. Alberto is currently a full professor of materials science and the department chair at Stanford University. Alberto Salleo holds a laureate degree in chemistry from La Sapienza and graduated as a Fulbright Fellow with a Ph.D. in materials science in UC Berkeley in 2001. From 2001 to 2005, Salleo was the first postdoctoral research fellow and successful member of research staff at Xerox Palo Alto Research Center. In 2005, Salleo joined the Materials Science and Engineering Department at Stanford, and as an assistant professor in 2006. Salleo is the principal editor of MRS Communications since 2011. While at Stanford, Salleo won the NSF Career Award, the 3M Untenured Faculty Award, the SPIE Early Career Award, the Tau Beta Pi Excellence Undergraduate Teaching Award, and the Gores Award for Excellence in Teaching, Stanford's highest teaching award. He has been a Thomson Reuters highly cited researcher since 2015, recognizing that he ranks in the top 1% of cited researchers in his field. Really excited to hear his talk today on plastic-based sensors for wearable technologies, fundamentals and applications. So really lucky to have you today, Alberto, and I'll turn it over to you. Thanks so much.
Thanks, Ryan, for the invitation and for the very kind introduction. So what I will talk about today is our work on using polymers in electrochemical devices. And there's many applications of polymers in electrochemical devices, but the one I'll talk about today is wearable biosensors. So I'll start with the acknowledgement page. Here's a list of students and postdocs in my group that contributed to this work. In particular, big thanks to Onur and Scott who started this. Sheita was a master's student, a very talented master's student in the group, and Melissa and Quentin are keeping the work going in the last few years. And then a number of collaborators, mostly here at Stanford, in particular the Bao group, the Merman group, and the Melange group, and a list of funders. And the two more important funders are PHIND and BICI USA for this particular work. So I want to start with a little bit of a general introduction and sort of the building blocks of what we use for our sensing technology. So the first building block actually is the transistor, and this is our most fundamental building block. And I will not talk a lot about device physics, but essentially you can think of a transistor as a valve that shuts down current. And so you can have the valve being closed and current doesn't go through it, or you can open the valve and then current goes through it. And you can see right away how this is applicable to sensing, because if what makes a valve open and close is an analyte, you can see how this easily turns into a sensing device. Now, the materials that we work with are more unconventional at your classic transistor materials, which would be silicon. All your computers are made with silicon transistors. And we work with polymers for a number of reasons. One of them being that these polymers work very well in electrolytes. And what we want to sense are analytes that are dissolved in electrolytes. And so we want something that's compatible with electrolytes. And the main material that we use, although we're moving towards other material system, is this blend of two polymers. One polymer here, the one at the bottom that I'm indicating now, is called PDOT, and it's essentially a semiconductor. So if it doesn't have any charges on it, it's an insulator, but if you put charges on it, it will start conducting electricity. And this polymer is blended with this other polymer, which is called PSS, and this is a polymer that's an insulator, but it has the particularity of carrying negative charges, a certain amount of negative charges. So when you blend them together, because the PSS has a negative charge, this has to be compensated, and it's compensated by a positive charge on the conducting polymer. So the negative charge cannot move because this polymer, the PSS, is an insulator, but the positive charge on the PDOT can move. So you see in this cartoon what this means, that you have a big, you can think of a polymer as this big chain with once in a while a negative charge on it, and it's immersed in a matrix, even though that's not really how it works, but you can think of it that way. It's immersed in a matrix of this other polymer that has a positive charge, and the positive charge can move. So essentially this blend is a conductor. So if I put a voltage across it, it will conduct because my conducting polymer, my semiconducting polymer, sorry, is doped by holes. So it's p-type doped when it's blended with this PSS. So how does this work in a device that can sense? So as I told you, this polymer can works well in electrolyte. In fact, it soaks in the electrolyte. It's like an electrolyte sponge. And this is due to the fact that this particular polymer has these negative charges, and so it's hydrophilic and water can come in. So if I put my polymer film and I put an electrolyte on top of it, and then I immerse an electrode in the electrolyte, I can push electrodes, I can push ions in and out of this polymer. So if I don't do anything, I don't push anything, remember this is a conductor. So if I put a voltage between this terminal here that I call the drain and the ground, which I call the source electrode, I will get a certain current. It's not an ohmic conductor, but it's pretty good, as you can see. You get milliamps type of currents. So now imagine that I put a positive voltage on this gate, which means that it repels the cations, and the cations will come into this film. So now remember that this film is conducting because there's anions on the PSS that are compensated by mobile holes on the P dot. So now if these anions are compensated by cations, I have fewer mobile holes, and so the current is suppressed. So by putting a positive voltage on the gate, I'm reducing the current between the source and the drain. And conversely, if I put a negative voltage on the gate, I'm injecting anions in the polymer. These anions must be compensated. They'll be compensated by mobile holes, and so my current goes up. So you can see that depending on the voltage on the gate, I am modulating the current between the source and the drain, and that's called the transistor effect. So if I pick any gate voltage here, I just showed you 3 gate voltages, but I can pick any gate voltage in between, I get any current in between. And so now if I fix a drain voltage and I look at the current as a function of gate voltage, you see that it doesn't change. Even if my stepping gate voltage is constant, it doesn't change in a constant fashion. The ratio of the changing current to the changing voltage is called the transconductance, and that essentially is a measure of how this device amplifies a signal, right? Here, it amplifies most because you have the biggest change, the biggest bang for your buck. Here, it amplifies the least. And so the transconductance gives you an idea of how this device amplifies. And so you can see right away the making of a sensors here, right? As a sensor, because if I put ions in this electrolyte, I can push them in and sense them by looking at a change in current. And on top of that, in principle, I can amplify the signal because of this amplification effect that's given by the transistor. The transistor is a built-in amplifier. So you can see right away there's 2 advantages here, sensing and amplification all built in. You'll see later that I will challenge this assumption, but right now you can take it for good. So here's the advantage. This what is called the electrochemical, organic electrochemical transistor. It's organic because it's made of polymers. Polymers are made mostly of carbon and hydrogen. It's electrochemical because it works by pushing ions in and out, as opposed to the field effect transistor, which works by putting electric fields and having electronic charges being compensated. So it can act as a transducer of ionic fluxes into electronic fluxes, because that ion flux that went into the P.PSS channel is sensed by an electronic flux that goes across. And so it's a really nice transducer of an ion flux, which electronics doesn't really know how to deal with, into an electronic flux, which electronic knows how to deal with. That's what we do electronics with. For this reason, it can be easily integrated into an electronic circuit because it sort of speaks the language of the electronic circuit. And in principle, it can be miniaturized easily, just like you can miniaturize regular transistors. Now, the challenge is if you want to use this as a sensor is that it's not selective at all. I just showed you that if I have a cation that gets injected in the channel, it modulates the current. So any cation will do. So it's not selective. And so far, it's only sensitive to ions. And we may be interested in sensing things that are a lot more complex or different than ions. So our first order of business is to turn this interesting device into something that is selective and that can sense things that are a little bit different from ions. So in order to make it selective, we use these ionophore membranes. So these are molecules that have pockets that are the size of the ion that you want to sense, and that way you can be selective towards certain ions. In order to sense things that are not ions, we'll actually use other polymers that are known for synthetic biorecognition. Sometimes people call them plastic enzymes. So let's start with the polymer ionophore. So what you do is you have this molecule, for example, nonactin is an ionophore for ammonia. So if you want to sense ammonia, you integrate this nonactin molecule in a plastic or in a polymer membrane. So this is not the same polymer as my transistor because that has to conduct current. I don't want to put strange stuff in it. But I will have another polymer, in this case it's PVC, polyvinyl chloride, as a matrix, and I'll put these little molecules of nonactin. And the idea, at least at a cartoon level, is that if ammonia is on my electrolyte here, it will get captured by this pocket, and if I have enough of these, it can be shuttled through. The reality may be a little bit more complex, and we don't really know the exact mechanism of how this works. I suspect actually what happens is that this ammonia just gets trapped here, and the charge gets sensed underneath. But for the purpose of a sensor, that's not that important. All we need to know is that this hopefully will act as a selective and sensitive membrane just for ammonia. This will allow us to turn our all-purpose ion sensor into an ammonia sensor. And in fact, these type of molecules and membranes are used in electrochemical electrodes that are selective. So we know this works. So far, this is not particularly exciting. The interesting thing here is that we're integrating this in a device that can then be integrated easily in electronic circuits. And so what we do, sorry, let me go one step back, is that we will put that membrane between the electrolyte and the channel. And so if the ammonia wants to go through, it will have to go through this membrane and it will be sensed, and any other ion will not be able to go through and will not be sensed. And so I show here that this works as advertised. When we change the concentration of ammonia, the response of the device is changing. And this is plotted upside down. The more ammonia I have, the less current I have. Current is 0, is up here. And that's because, remember, if I inject cation in my polymer channel, I have to compensate by having fewer mobile holes, which means less current. And so you see here that as a function of a concentration of ammonia, if I put a pulse on, let me go back here. If I put a pulse on this gate electrode, the ammonia goes through, it compensates for the PSS negative charge. I have fewer holes, and so I have less current here during that pulse. And so you can see it very nicely. More ammonia, less current. Remember, this is upside down. So I can then plot a calibration curve, the change in conductance of my channel as a function of a concentration of ammonia. And you can see that that change in is proportional to the logarithm of the concentration of ammonia. So you can use the change in conductance or the end of the pulse as a way to measure of ammonia. So one important thing is you want to know whether this sensor is also selective. And so you put other ions in solution that are interference in the potassium. And as you can see, as a function of a change in current, which is the same thing as a change, if I put and doesn't get interference from other cations that I might have in my electrolyte. Now, another thing you can do is if you're interested in something, oops. If you are interested in other ions, there is what are called selectivores for a bunch of other ions. For example, there's a calcium selectivore that's very well known. Here it is. So I can now make my ion selective membrane also for a divalent cation, in this case calcium. So it's the same principle. I have my triangle here. Top of it, I have my electrolyte here. I put a pulse on the gate. The cations, a positive pulse, the cations will try to cross the membrane. The only cation can cross the membrane is calcium. So I get a change in conductance if I put calcium as a function of a concentration of calcium. And if I change the concentration of sodium or potassium, I actually don't get a change in the current. And so you can see that I can then calibrate my sensor as a function of concentration of calcium from low to high and high to low. So this is also important to show. This is a reversible sensor, and so it works as a reversible sensor. Sorry. And here this is a mistake. Sorry, this is taken from a paper. This should be ammonium. These are the wrong curves. I apologize. So, like I said, one nice thing is that you can integrate this pretty easily. And because these are polymers that can be patterned and deposited very easily, you can make sensors very cheaply. So what you can do is you can deposit by inkjet printing, for example, silver. This can be done routinely nowadays. And then you can chlorinate, you can make the silver react and it turns into silver chloride. So you can make your silver chloride electrode the same way. Then you can mask the silver chloride electrode. This is a gate electrode. You deposit your polymer, you deposit your ion selective membrane, you unmask the silver chloride electrode, and now you can make very easily this sensor with very simple fabrication techniques. And because the device itself is always the same, it's always this transistor that has the P.PSS, this is a semiconductor, and then the two electrodes and the gate electrode. The only thing that makes different devices is the ion selective membrane. You can multiplex your system and have one device that is an ammonium selective membrane. The device next to it is a calcium selective membrane, that you could have a sodium selective membrane, and so on. And so this is what we wanted to show, is that you can make very easily multiplex sensors, and you can make them, because this is all by inkjet printing, you can make them on flexible substrates. So and we wanted to sense sweat. And so this is how we went about doing it. We had a waterproof protection layer. Then here is our device layer. And then we wanted to collect sweat. So we had a little reservoir layer, essentially sort of a space that's available to be filled with sweat. And for the sweat to wick in, we made a layer of another polymer with tiny holes that would wick the sweat in. And to make these holes, these are probably the most expensive holes in the world. Of course, there's better ways of doing it, but we had a femtosecond laser in our lab. So we use a femtosecond laser that allows you to make very, very well-defined tiny holes. And so the sweat wicks through these holes, gets into this reservoir, is sensed here by these sensors. You don't see any electronics because we didn't really want to build the electronics on board. The idea here was just to show the sensing device. So these electrodes then go out to the outside world. I want to be really transparent about this. This is not really a fully integrated system. These go out to the outside world and are connected to all the electronics in our lab to put in the gate pulse and then measure the current between the source and the drain. So this is what it looks like on the arm of my postdoc. Again, collecting sweat is not really our specialty. So this was not a particularly good way of collecting sweat, which means a postdoc had to go out for about a half-hour run. So they would have enough sweat in the reservoir for us to be able to sense it. Then you put the gate pulse, you see the change in current. And then after you build the calibration curve, this change in current can be translated in a concentration of ammonia. And to make sure that our measurement is correct, we then measured the concentration of ammonia with a standard electrochemical electrode, and our measurement after the calibration is just about as good. And we did calcium at the same time, same thing. After we put a pulse for about 30 seconds, measure the current at the end of the pulse, and the current is then translated into a concentration of calcium after the calibration curve is built. And then we check with our standard electrode that the concentration of calcium is what you expected based on what you get from the standard electrode. It takes 30 seconds for the signal to build up because these devices are very large. These are not made by any microfabrication technique. Because they're large, it takes a lot of time for them to charge up with ions. They have a big capacitance, so it takes a long time, and that's why it takes 30 seconds. But this is not a limitation, intrinsic limitation of the device. In fact, we're working on making the device smaller and smaller, which makes them faster and faster, and also allows you to cram more devices in a smaller space and have a truly multiplex system that allows you to measure multiple things at the same time, not only two, on a relatively large patch. Another thing you can do is if you can sense ammonia, you can also sense other molecules that are degraded into ammonia by a reaction with an enzyme. So for example, we wanted to sense creatinine because if I remember correctly, creatinine as an indicator of some renal diseases. And so creatinine deaminase degrades creatinine into product and ammonia. And so if you have creatinine and a deaminase nearby, you can sense ammonia, and that's a proxy for creatinine. So what we needed to do, we needed to immobilize the creatinine deaminase near the ion selective membrane. And it turns out the easier way to do this was with BSA, and then the creatinine deaminase was deposited on it. And this immobilized it for a while. And again, this is not really the best way to do it. We just wanted to demonstrate the concept that if you have an enzyme that degrades the desired molecule into an ion that you can sense, sort of expanding a little bit this ionic sensing, you can sense that molecule. Again, full disclosure, the creatinine deaminase after a while desorbs from the BSA, so this is not the best way to do it, and also degrades after a while. So there's other ways, there are better ways of doing it, but this was a nice demonstrator that you can use an enzyme as well with this type of device, which is not obvious because you have here a big barrier layer, so you might wonder whether this will interfere with the operational device. It turns out it slows it down a little bit because there's a little bit of a barrier now for the gate signal to go down, but it doesn't significantly degrade how the device works. So here's the result of the experiment as a function of the concentration of creatinine. You get a calibration curve, and so you can measure the concentration of creatinine, in fact, by measuring the concentration of ammonia with this type of device. And if you have no enzyme, you actually get no response to the concentration of creatinine. And the interference here, again, sodium and potassium don't really do anything because we have our ammonia ion selective membrane that is always sitting on top of the P.PSS. Now you wonder whether the ammonia itself would be an interferent. And it turns out that it actually isn't a big interferent because this BSA actually creates a barrier for the ammonia that comes from the solution into the membrane. So you really are more sensitive to creatinine than to ammonia. So ammonia interferes a bit, but if you had an ammonium sensor nearby, you would be able to subtract the ammonium signal from the creatinine signal, actually get the creatinine signal. Okay, so that's for ions, pretty straightforward. We essentially adapted ion selective membranes that are very well known in the literature for electrochemical sensors to our electrochemical transistors. So sort of a different way of sensing, but the sensing layer is well known. What about molecules that are not charged? And in particular, we were interested in small molecules, hormones in particular, and cortisol is one that we zeroed in on for being interesting. And it turns out actually after we published our work on cortisol, we got a lot of interest, and I still get years later a lot of interest into commercializing or whether these sensors are commercial. So here's cortisol, and the reason why we got interested in it is because it's called a stress hormone. So it's a potential biomarker for physiological stress, and we hear lately a lot about stress. And so one would like to measure stress during the course of the day to maybe tune out, do some relaxation or whatever it is, because sometimes we're not aware of the stress, but our body is actually stressed out. It also plays an important role in regulation of various physiological processes, including blood pressure, glucose levels, carbohydrate metabolism. And there's a number of conditions that are associated with high cortisol level or low cortisol level. Now, the reason why we're interested in this also is that measuring cortisol as a spot measurement is not that interesting because it has a circadian rhythm. So this is sort of ideal for wearables because there you have the device on you and you would want to measure cortisol maybe every 10 minutes so that the number that you have, you know that is not due to the circadian rhythm, but it's actually a deviation from the circadian rhythm. And so this is kind of an ideal application for a wearable system where you want to take measurements over the course of the day so that you can tell whether something is off compared to what you expect with your normal circadian rhythm. So how do you measure cortisol if your sensor is really an ion sensor? Well, one way would be, let's see if there is any other degradation reaction with an enzyme that would turn cortisol into something charged or would produce something charged as a byproduct. And we actually couldn't find any enzyme-related detection mechanism. Cortisol itself is not charged at physiological pH, and it's not related to any secondary charged ion. In fact, we didn't really like the idea of going on an enzyme anyway because of the reasons that I told you. They degrade, especially for wearable systems, it's not ideal. And also they desorb. It's pretty hard to have them bound to something and maintain their functionality in a reproducible way. So what we need is a specific biorecognition mechanism that allows to sense selectively this non-charged small molecule. And what we fell onto is a class of molecules that are called, they're not molecules, class of materials that are called molecularly imprinted polymers. So this is a technique that was pioneered by Klaus Mosbach to generate what are called biomimetic synthetic receptors or plastic enzymes that have different names. And the idea is simple but really brilliant. You have your template molecule that has a certain shape, and we know that molecular recognition really relies a lot on shape, but also some chemical binding. And you have some functional monomers and a cross-linker, and the monomers will sort of mold themselves to the shape of the molecule, and the cross-linker will polymerize them. And if you have the right elution solvent, it will remove the target molecule and leave a pocket that's shaped like the target molecule, and maybe has even some non-covalent interactions preferential with the target molecule. And so you essentially form, molded in a polymer, an enzyme. That's why these are called sometimes plastic enzymes. These have been known for quite a while. I'm not aware of any commercial application that uses them. Maybe there are nascent ones, but I think they're a really interesting system. And so we make our molecularly imprinted polymer. These are particles. This is what they look like. They have a lot of pores. And then what we make is also a non-imprinted polymer where we use the same molecules, but we don't use a target molecule. So we have the functional monomers, the cross-linkers and all that, but no template molecule. So there's nothing to mold around. So these now have a much lower surface area, as you can see. And then same principle, we put this molecularly imprinted polymer between the gate electrode that's going to push ions in the electrolyte and our device. So the idea is that our electrolyte contains the cortisol, but also contains other ions. And in principle, if the molecularly imprinted polymer binds to our cortisol, these other ions cannot make it through. And so even though we're not sensing the ions per se, the ions give us a sensing mechanism. On the other hand, the non-imprinted polymer should just be a barrier and not let anything through. So this actually, so here's, our recipe, cortisol. This is the monomer. This is the cross-linker. This is called the initiator that initiates the cross-linking. And actually, a very important part of this is the solvent, because you need a solvent that allows you to make these high surface area polymer particles. So you need what is called a porogenic solvent. And this is actually pretty messy, because the way you make this is you make this molecularly imprinted polymer. It's quite brittle. You make it in a vial, and then you break it and you grind it into these particles. And then these particles are integrated in a membrane similar to the one that we use for ion sensing. So the PVC membrane, it has these particles dispersed in it. And there's probably a lot of engineering that goes into optimizing that. We haven't really attacked that quite seriously. And so here's how the device works. So you have a concentration of cortisol. And so in this case, when you have a lot of cortisol, you're blocking the pores. And so the cations cannot get through. And so you don't get a big change in current, because you're now blocking the cation, so there is no modulation in current. On the other hand, when the cations can make it through, you get a big modulation in current, because when the current gets suppressed by the cations. So this is a little bit backwards from before, but the sensing principle is always the same. It's a cation that get into the device and suppress the current. So you can, of course, you want to see if the sensing is reversible. So you go from low to high with the red, from high to low, and there is a pretty decent range here of reversibility. The control membrane is the one that's non-imprinted, and you see there is no response. Another interesting thing that you can do is you can see how selective it is. So you have, this is cortisone, and you have some structural analogs, progesterone, testosterone, cortisol, progesterone, testosterone, and cortisone. And as you can see, these actually don't generate a big response, and you wouldn't expect them. You wouldn't expect them in significant concentrations anyway, but it's good to know that they're not big interference. So this seems to work quite well as a sensor. The range is not that great. The response is not that great, but we haven't really engineered it a whole lot. Now, well, I'll talk about the mechanism maybe a little bit later. So we wanted to, again, show how this works in sweat. So here's my postdoc's arm. It's the exact same picture as before. Sorry, I recycled the picture. And to calibrate the device, what he did, he made artificial sweat. So there is actually a standard for artificial sweat. He sprayed it on his arm, and then he calibrated with different concentration of cortisol in the artificial sweat. And then he went out for a run, and then he measured the cortisol. So then he went back to the lab. Again, no electronics on board here, connected this to all our electronics, measured based on this calibration curve how much cortisol he expected. Then he took the sample and measured it ex situ, still with our device, but not on his body. And then he also measured it by ELISA, which is a standard method. And you see our measurement is off by maybe 20, 30%. So we're not that far off. So this is quite encouraging for a first attempt of a measurement of cortisol on body from sweat. It turns out you can measure it also in other in other fluids. For example, people are also interested in measuring cortisol from saliva. I think the correlation factor with serum is quite high. So we also measured from saliva, collected saliva, and then measured cortisol from it. After the calibration curve, it turns out the subjects were in the healthy level. And again, this corresponded quite well to what we measured by ELISA. Now, the reason why we like this molecularly imprinted polymer method is that it's because it's really general, right? Once you have a small molecule, and there's recipes for molecularly imprinted polymers for a lot of small molecules out there. It's a little bit of a black magic, so this is something we want to explore a little bit better in the next few years. But you find recipes to make molecularly imprinted polymers around pretty much everything, even very large molecules. Now, for very large molecules, it doesn't seem to work very well. It seems like the sweet spot is a few hundred Daltons. So small molecules like these hormones seem to be ideal. So we had summer students. This is done actually by undergrad summer students supervised by the postdoc. So we use estrogen now, built the molecularly imprinted polymer around estrogen, and we were able to sense estrogen as well. So what we like here is that the molecularly imprinted polymer is what makes every sensor different from each other, but the platform is always the same. There's always this electrochemical transistor. So it's very easy now to imagine a completely multiplex sensor where you have 10 or 15 of these little sensors, and then they're each functionalized with a different molecularly imprinted polymer, and you can have a complete panel of sensors that will measure a whole range of things in a pretty compact footprint, which is one of the things we're really interested in doing. So to be able to do this in a compact footprint, you have to be able to fabricate sensors essentially by photolithography, which is what is used sort of the industry standard for microelectronics. I showed you how you can just by printing make devices, but printing really is not good to make very small things. You need photolithography to make very small things. And it turns out that we have two processes that use photolithography to make these devices. One is what we call a parylene-based process, where you use a parylene film as a masking layer, and then we rip it off, and that defines all the features. Or we actually have a process developed by Nick Melosh at Stanford that uses all standard equipment in our clean room. This parylene process uses some equipment that is not standard. But the bottom line is that we can make arrays of these little sensors, and these look like electronic chips. And so now you can imagine having, you can see here all these pinouts, you can imagine having 10 or 15 of these sensors. And this also becomes important when you want to be more quantitative, because you'll always want to have some dummy devices, some reference devices. Because remember, I told you, you sense by looking at how many cations come from the electrolyte. But if the electrolyte changes concentration over time, that will change as well. So you'd always like to have some dummy devices that essentially measure the conductance of the electrolyte. That way you can take that into account in your measurement, in your calibration curves. So to turn this into a real sensor, it's actually quite a bit more complicated, but being able to have a lot of devices near each other helps a lot. So this is a process we developed for rigid substrates, but I told you that we're interested in wearables, and of course, rigid substrates are really not ideal for wearable technologies. So we wanted to develop a similar process that would work on flexible substrates. And so the idea is you have your substrate, and then you coat it with polyimide, which you can spin coat, and you deposit everything on it, and then eventually, for example, your metal. So here is your metal layer. Then you put your photoresist, you define your photoresist, you etch down, you strip the photoresist, and now you have your metal traces. And that's just a metal. Now, then we have to put the polymer. And actually the challenging part in reality is the polymer, because it seems trivial to adapt a process that's used for silicon to polymers, but these polymers actually get completely destroyed by the chemicals that are used in the silicon process. So we have to come up with a process that uses the same chemicals, but doesn't damage the polymer. Otherwise, this is not going to be really scalable. But even this very first step actually turned out to be quite challenging. Once we peeled the polyimide, this metal had built-in stress, and that stress ripped the polyimide apart. So the first thing, not rip, but made it curl, sorry. So the first step was to figure out how to make sure the polyimide didn't curl, and that took quite a while, but there's somewhat standard ways of doing that. One is you make this very thin, so it doesn't develop a whole lot of stresses when the metal is deposited on it. And then you use adhesion promoters and all sorts of other tricks to make sure that this then doesn't develop any stresses when you put the metal down. Eventually, we were able to have it so that you could have metal traces without the polyimide curling. But really, but yeah, in the end, this was never perfect. You can see it here, it's still curled a bit. And so the idea is, well, if you put something on top of it that will curl the other way, it will keep it sort of under mechanical equilibrium. So we put another polymer on top of it, but now you have a polymer on top of it. You want to be able to access the region between the two electrodes to put your sensing polymer in between, so you can measure the conductance between the two electrodes. So you have to do what is called opening a window or cutting a window. Once we did that, actually it was even worse, because this polymer, which was different so they could be photo-defined, had a different thermal expansion coefficient on the polyimide, and so this curled it even more, because now rather than just having two small metal lines, we had a whole layer on top that made it curl. And so the solution, as you can imagine, is to use the same polymer top and bottom. So we developed a recipe to use polyimide top and bottom. So there is a polyimide layer, then you define these two metal layers, then you put a polyimide top, and then you put a protective layer so that you can cut a hole into the polyimide. Then you put your photoresist, you cut the hole into the polyimide. So first this protective layer is a metal, you etch the metal, cut the hole, remove the metal, and actually this works beautifully. As you can see, we can make these coupons that are sort of chips, but they're not now on a rigid substrate. They're all on polyimide, so they're flexible and they can adhere to the skin, and we can make entire wafers of it. Right? So people can do this by printing, but we can actually make it on wafers using all equipment in the SNF that's completely compatible with standard silicon processes. So this is in principle scalable, just the same way you can scale the fabrication of computer chips. But now is the challenging part, which is to deposit the polymer between the sensing polymer between these two electrodes. And so the way to do it is you deposit the polymer, and this is a process developed by Nick Meloche, and then you put a protective layer on top of it. But the protective layer has to be quite delicate as well. You have to be able to remove it in the end without damaging the polymer. It turns out germanium is a great protective layer, because germanium oxide is actually etched in water. So that's a very gentle etch, but germanium itself is quite resilient. So we deposit a layer of germanium everywhere. And then we do our photolithography. So here's a photoresist. It gets patterned to reveal essentially the channel. Then you etch the germanium. This is a dry etch of the germanium. So you go down to the sensing polymer, but now you want to remove this part because you only want to sense here in the channel. So you etch with oxygen. So the germanium etch is one chemistry. It's carbon tetrafluoride. The polymer etch is a different chemistry. It's oxygen, so you just essentially ash it away. Then you remove the photoresist, you strip it, which would destroy the polymer, but the polymer is protected by the germanium, so the polymer survives. And then you strip the germanium with water, and now you're left with your device. So this looks pretty simple. It's 2 slides, but this took several months to develop. And eventually we were able to make these chips. So here you see, actually this is designed by Yasser Khan in the Bao group. This is to collect sweat and see how fast you sweat. And here's our little devices. So here they are, big electrodes with small device. This is just a design that we went with, but of course you can change the design at will. Also notice that these electrodes have to be completely insulated because there's electrolyte on top of it. If the electrolyte touches the electrode, all your current will come from that process, and you also have some electrochemistry going on. So this is all covered except this tiny little opening where you have a little bit of polymer, and that's your sensor. And now, because we can make multiples of them on the same chip, here you have 4, we're able to show that we can sense sodium, calcium, and ammonium on the same chip. So you see here the calibration curve, the changing current as a function of concentration. You can see that these are not very good sensors. There's a measurable changing current and it's reproducible, but it's very small. And that's due to the fact that we didn't optimize anything. In particular, the ion selective membrane was quite thick. And so this actually is a detriment to the sensitivity of the device. But this is something that can be improved upon. It's not trivial, but it can be improved upon. But we really wanted to show a proof of principle that we can use a completely silicon-based process to make these polymer-based devices that are actually sensors of ions. And so now you can imagine making this in a smaller form factor, so we can make them now micron size, have a lot of them next to each other, and so have a lot of sensors next to each other and being able to sense in a multiplex fashion almost anything you can imagine in your sweat. So the sensing modality that I showed you is using a transistor and something that essentially modulates the response of the transistor by impeding more or less the flux of ions. But there's different modalities that can be enabled by these polymers. That's why we like them. They're very, very versatile. So one modality is what is called impedometric sensing. So you just measure the impedance of an electrode that's made with a polymer to the electrolyte in the presence of an analyte. And in principle, if you have more or less analyte, that impedance changes. You're left with a problem of selectivity, but you know how to address that now with the ion selective membrane. So this is very simple. In principle, measuring impedance is very simple. You send a sinusoidal wave, a little voltage, and then you measure the current that comes out. The problem, though, is that this depends on the impedance of the analyte as well. This is a mistake. I should say depends on the impedance of the electrolyte. So you need to have a reference device next to it, and it's not very selective for that reason. Another way to sense is Faradaic. So essentially you have your target molecule and then you have it land on an electrode and you oxidize it or reduce it, so that will produce a current. So you measure the oxidation or reduction current of the analyte to an electrode. This is a very well understood and known way to do electrochemical sensing. People know how to do it selectively by using, again, these ion selective membranes, for example, or using enzymes. One of the problems, it produces very low currents, because if you work out the math of the typical concentrations of analytes that you'd have in sweat or even other fluids, and what currents these would give rise to in a Faradaic process, you're sort of in a fraction of a microamp. Now, if I'm in my lab, a fraction of a microamp is very easy to measure. But if you want a portable system or a wearable system, that becomes more challenging because there's a lot more noise in those systems. And so you want actually larger currents. And this sounds now like when I said, oh, you have a transistor that amplifies, this now sounds attractive, because if you can do it with a transistor, you get the current and the amplification. And this was, in fact, historically a big drive towards using these electrochemical transistors for sensing. Is the idea, the intuitive idea, that the transistor would do the sensing and the amplification in a single device. And I'll show you in a minute that that is actually not a true idea, but we found a way around it. But let's start with impedometric sensing. This is very simple. So this is work done by Nick Melosh. We collaborated by making the molecularly selective membranes. So they have these 15 micron platinum iridium wires, and then they electropolymerize the polymer, the P.PSS, rather than depositing it by spin coating like we do. They put the electrode in a solution that has the monomer, and then you pass a current and this polymerizes on the electrode. So it's very handy. And then we helped them put together this molecularly selective membrane. So they dip coat into a PVC solution that also has the molecularly imprinted polymer. So if I look at a cross section here, I have my wire, the P.PSS, the selective membrane, and the P.PSS is needed because it reduces the capacitance, it reduces the impedance of the whole system. So it gives you a higher response system. And also the molecularly selective membrane adheres better to the P.PSS. And here's where your analyte sits. So then you'll have another electrode somewhere else that will put a voltage, and you'll measure the impedance between the gate electrode and the P.PSS actually, and the platinum microwire. And so if ions cannot make it through, the impedance of this whole system will go up. And this is how it works. If you measure the impedance as a function of frequency, you can see that systematically, as you increase the concentration of cortisol, the impedance goes up. Again, not super sensitive, but definitely measurable, and not super sensitive because NOFAR didn't work super hard on making it very sensitive. In the end, what you want is sensitivity in a reduced range, because cortisol will not go. Sorry, this should be nanomolar with a capital M, because cortisol will not go to very high concentration. So you want to tailor the device for the right concentration. We haven't really looked very much into that, but it's certainly feasible. Not super sensitive again, but it works. Interestingly, the mechanism by which this works is not entirely clear, because if you look at the cross section here, you actually don't need the ions to cross the whole membrane to give you a signal. And so this led Nick, in fact, thinking that maybe our understanding of how these work is not really good. And he has other ideas of how the molecularly selective membrane works that are speculation, so I'm not really going to go into it. But the interesting fact here is that by building a different device and operating it differently, we're sort of learning also how these molecularly selective membranes work. The idea that there were pores that were clogged by the molecule and the ions couldn't never make it through never sounded right to me either, because the ions don't, they're always going to find nooks and crannies to go through. A molecule clogging a pore is not really going to do it, and maybe it will increase impedance, but it's not going to do it completely. Now back to actually Faradaic reactions. We're really interested in these lately, so I want to talk a little bit about these. So, well, if I have a Faradaic reaction in this device, because it's a transistor, it will amplify the current. But if you think about it a little bit more, you realize that that actually cannot happen, because if you have a Faradaic reaction, this will create a certain gate current, because there is a reaction either with the gate or with the channel. It doesn't really matter. The argument works both ways. So if you have a Faradaic or redox reaction with the gate, because you put a gate pulse and this molecule in here oxidizes or reduces, well, because it's a closed system by current continuity, the same current has to go through a channel. And so in fact, we measured it. If you measure the current and the drain as a function of the current on the gate, you don't get any amplification. In fact, you get a slightly lower current in the drain, because some of the current has to go through the source as well. So in fact, if the device is perfectly balanced, you get about 50-50 current, but in fact, you don't get amplification. You get less than one amplification factor. Amplification factor to me is a current detected on the drain divided by the current detected on the gate. Right? The current on the gate is the reaction current, the analyte that's reacting. The current on the drain is a sensing current that I sense in the outside world. So ideally, I'd like that ratio to be much higher than one. But simple physical argument to realize that even though this is a transistor, you're really operating it as an electrode. By current continuity, you cannot get any amplification. So this means that you have currents that are less than a microamp. You know, that's fine if you're in a lab, but if you want something that's portable, that is really not a good situation to be in. The electronics become a lot more challenging. So the way to get amplification is actually to separate the reaction from the amplification. And if you think about it, this is just sort of good engineering practice. You don't want one device to do 15 things, because it will not do any of them very well, and it becomes difficult to optimize. You want the amplifier to work as an amplifier, so you want the transistor to work as a transistor, and you want the sensor to work as a sensor. So this is a very basic idea, but amazingly, people hadn't thought about it. You separate the reaction cell from the amplification cell. So what happens now is that when you have a Faradaic reaction here, this electrode acts as a gate for the transistor. And so now it's not the current that gets transduced here, it's a voltage. And so the transistor operates in a potentiometric way, and that's how you get amplification. So if you have now a gate current, this changes the potential of this electrode because it's charging up because of the gate current. And this gets now amplified in a drain current. And once you make the device, you actually get an amplification factor of about 1,000. So the same current that before was a microamp, if I did everything in one device, becomes now a milliamp if I do it in two separate devices. And because now we know how to miniaturize all this is not significantly larger than just a sensor, right? Okay, it's going to be twice as large, but it's still a very small device. So this is a very convenient way of doing things, because you get amplification and sensing. And to show this concept also, that the fact that you have the two compartments that are separate, again, this is good engineering because it allows you to optimize things for what they're best at. So in the reaction compartment, for example, we use glucose, the sensing of glucose as an example, not because we're interested in sensing glucose, but because it's sort of well-known and simple. So when you have glucose that gets oxidized and you have this cofactor, so what happens is the glucose gets oxidized and it generates hydrogen peroxide. Well, the hydrogen peroxide is an oxidant, and so it can steal an electron from this electrode in the reaction cell. So it can oxidize this. So this increases the potential of this. But on the other side, the cofactor that got reduced can itself get oxidized and reduce the other electrode. So donate an electrode here. So this becomes more positive. This becomes more negative. So I get twice the bang for my buck. My glucose molecule, if I only use the reducing electrode, I get a certain change of potential, about 200 millivolts. If I only use the oxidizing electrode, I get about 100 millivolts. If I use the two together, I get the sum. So I get a 300 millivolt, change of potential, which then makes my transistor swing by orders and orders of magnitude. So now I get a much, much more sensitive amplifier as well. So I've optimized the sensor and I've optimized the amplifier also by making sure that the largest transconductance, the biggest amplification, occurs in this potential range. So I can optimize a transistor to get the biggest amplification, and I can optimize a sensor to get the biggest voltage swing. So I think these electrochemical transistors can become part of what I call the ubiquitous computing paradigm. Before, as Ryan said when I introduced me, before coming to Stanford, I was a postdoc at Xerox PARC, and that's the birthplace of UbiComp. And I really like this sentence by Mark Weiser, the late Mark Weiser, who was the inventor of UbiComp. The next computing technology is UbiComp, or the age of comp technology, when technology recedes into the background of our lives and you don't even know that it's there. And these transistors and sensors, I think, are a great way to introduce sensing that is not traditionally done well with conventional electronic devices, but making an interface with conventional electronic devices. Sort of the electrochemical transistors are a great bridge device between conventional electronics and human physiology. So you can imagine all sorts of wearable devices, but also devices that are integrated into everyday objects and sense a bunch of things without you ever actually knowing that they're doing it. So I see that I'm running out of time, so I'll just put my summary here without really reading it, and I will be happy to take any questions. Thank you for your attention.
Thanks so much, Alberto, for a really excellent talk. So please go ahead and type your questions in the Q&A or raise your hand to ask questions directly to Alberto. I guess just to start us off, kind of, what form factor are you envisioning? I mean, you showed kind of a patch. You also mentioned, you showed a lot of others. What do you, in terms of, I'm thinking of form factor as well as placement, in the body.
So, I mean, we decided to work on patches because we have this process to make things that are flat, and we like that form factor. But I think it's a limitation of our creativity. These plastics are moldable, so you can imagine all sorts of shapes that you could use. You can integrate them in handles and other things. In fact, there are groups. I didn't talk at all about the power part of this, right? So you need batteries and all that. And so there are groups that are doing some really interesting work where they use actually polymer-based batteries that are also structural. So the structure of your object is also the battery, and the sensor is integrated in it. So to answer your question, we think of patches because we started working also thanks to PHIND on sweat sensors and so on. So we think of things that you put on your body. But that's really a limitation of my creativity. And in the end, you could integrate this in all sorts of objects quite easily.
Excellent. Looks like we have a question.
Yeah. Hey, Alberto. This is a great talk. Very exciting. My question is, have you any experience using this to measure like an electron, just charge, like type of? I know you have been focusing on the ion, but I'm thinking using this to maybe measure electron beam or electron dosimetry or those kind of application?
Oh yeah, that's so that is definitely possible. I'll give you an example. I didn't think about, actually, no, that's not true. X-ray dosimetry is a great example. There's people working on using these same materials as X-ray sensors. When the X-ray strikes it, it generates electron hole pairs, and then you just collect those, for example. And it works quite well as well.
Okay, yeah, maybe I can follow up with you by email. Or, yeah,
sure.
so
yeah,
we work a lot on the dosimetry part.
Absolutely.
Thank you.
Daniel, please go ahead and ask your question. Oh, Daniel, go ahead if you like.
Can't find me.
Oh, I figured you were trying. Sorry.
I was going to ask a similar question. Can you use this as a oxygen sensor? Can you detect changes in oxygen with this technology?
Yeah, you can, whether it's so I guess, yeah, these polymers are unstable, they oxidize, so you can. Now it's not reversible, right? Once they oxidize, although I shouldn't say that, because if they're sitting on an electrode, you might be able to inject an electron and reduce them back. Never thought of it. We usually think of oxygen as a nuisance, but not really as something that we would like to detect.
Well, I think it'd be great to have a continuous patch to monitor oxygen concentrations, also use in dosimetry for radiation with oxygen consumption, part of the process of the high energy beams of radiation cause oxygen consumption. So it's something that's been widely studied in radiation, the effect of oxygen, and so a nice simple measure of it would be good, particularly if you can do it continuously.
So let me see if I understand this correctly. You're saying if someone is being irradiated, the effect of the radiation dose depends on the oxygen concentration. So you'd want
Very
to measure
strongly,
it.
yes.
So you'd want to measure it in real time during the radiation process.
Right, and now we're studying a new type of radiation, ultra-fast microsecond beams, and we're arguing about how they work. Are they causing radio protection by making normal tissues hypoxic by destroying oxygen during the radiation? And so we're all studying, well, how do you monitor oxygen concentrations in real time, for example, during such treatments?
I'd have to think about it. The tricky part would be to be selective. But there's currently no oxygen sensor that's able to do that.
Well, a lot of things being studied with fluorescence and phosphorescence, but so it's a tough problem. We use back to film dosimetry and back to Frick dosimetry of ferric sulfate changes, but it'd be nice to have another way of doing it. And this looks like a very nice potential approach, at least.
Interesting. Thank you.
Thank you. Excellent work. Very exciting.
Thank you.
I'm sorry, go ahead.
Just a quick, make it implantable, like implanted inside the tissue or body. I mean, right now it's all, on the surface, right?
Yeah. So the PDOT itself, actually, there's a whole group of people that work on PDOT being implantable because they want to use it, for example, to measure neuron activity. So the PDOT in itself is implantable. I don't know how long it stays. Originally, Neuralink actually was working with PDOT electrodes, and they moved away from them. So it is implantable. I don't know how long it stays, and everything that we have around it. I don't know the ion selective membrane. I'm not sure what it is.
Okay, thank you.
So we have another question. Says, can you comment on best ways to deposit specific polymers on specific sensor sites on a multi-sensor device?
Yeah, I see. That's question from Chris. Hey, Chris. So the transistor is always made from P dot, and so that's great. We have a blanket layer, then we pattern it into single devices. But as Chris points out, then if you want a calcium sensor here and a sodium sensor there, you have to now deposit different things in different places. And in fact, this is currently one of the limitations in terms of sizes. We're thinking about how to do that. I'm thinking like a spotter could be a good way to do that. But right now, we cannot do it by hand. And that is a limitation on the size of our devices. So very well, point very well taken, Chris.
It looks like Chris also has another comment. Clark, amperometric electrode for oxygen might be integrated in a similar sense as your potentiometric sensors. It is based on oxygen permeation through a fluoropolymer.
Okay, I'll look into it.
Okay, well, it's really interesting work. Really looking forward to seeing what you come up with in terms of improving the different parameters you mentioned and having multiple analytes being measured and balancing that for all the other optimizations you're doing. So really great work, super interesting, and thanks for sharing it with us today.
Thanks for the invitation. Thanks everyone for attending.
All right, thanks everyone. Have a great day.